to today's lesson. So today we're going to be busy with trigonometric functions, right? We've been looking at what does it mean to have a triangle. When we started with investigating triangles, we then went on to looking at some concepts that have to do with the theorem of Pythagoras, our angles, which were special angles, and two other different types of angles, which we said was the angle of elevation and the angle of depression. We then also went on to look at how do we solve 2D triangles using either ratios or using the trigonometric functions, or rather ratios we call them for now. But in this lesson, we're now going to call the ratios functions. But first we'll look at what exactly is a function, right? I think that's the big question that you should be asking yourself. What is a function? And how do we define it, and how do we see that something is a function? That's what we're going to be talking about. So stay tuned as I take you through this. So let's have a look at this. Now, remember, we always start with our concept map. We're going to look at what we call the parent graphs. There's going to be a vertical stretch of that and a vertical shift. Those are two different things. And then there's going to be what we call a Cartesian plane, which we're going to look at, some trig functions, and also some trig ratios. But for now, we're looking at the Cartesian plane and the trig ratios. Remember that trig ratios on a Cartesian plane with our previous lesson, we did look at this. We said that we're now defining them using the y and the r, the x and the r, the y and the x, based on the triangle that we are plotting on the Cartesian plane. So that's one thing that I need you guys to please remember, because that's what we're going to be using to try and talk about functions for that matter. Now, if we now continue with this and go to actually the functions, we first need to ask ourselves, remember, what is a function? A function is a mapping, right? When I say mapping, I mean when you're plotting all over your values of input values to output values. But the condition is that each input value must correspond to only one output value. So I cannot have input value maybe being the x, because you know that's normally our input value, and my output value is y. I can't have my x as 2, and then I have my y as 3, and I have my other y as minus 3, like that. That cannot be the case. That's not a function, right? But I must have only one input value that corresponds with one output value at the time. So please note that. Now, some terminology that we're going to be looking at is a domain and a range. With a domain, this is okay, I'm going to use the word range, right? But the range, I'm not talking about this range. I'm talking about from minimum to maximum. That's what the range is when I'm trying to define this. So domain will be a range, or let's say a set of values that are on the x-axis where the graph is defined, right? So this will be when we say x is an element of, we normally use square brackets to mean included, or we use round bracket to mean excluded, right? So if I say -2 up until +2, I'm simply saying that -2 and 2 are included, and my graph is defined between -2 and +2. But if I say -2 on the round bracket and +2, I'm simply saying it is between -2 and 2, excluding the -2 and the 2. Then lastly, the concept of a range will be the set of all the y values where the graph is defined. So they both mean the same thing, but one is one variable and then the other one will be a different variable. So this will also be y is an element of either square brackets or round brackets, depending on what is happening on your graph at the time. Now, with angles on the Cartesian plane, we're just going to try and look at this again. Remember, we said r becomes our fixed length, and then one end is at the origin. Remember, the origin is where they are intersecting. It moves in an anti-clockwise direction when we are trying to measure the angle between the x-axis and the r. And remember, if I show you this, it will look something like this when it's in quadrant 1. And if you rotate this from now 0 to 360, it will therefore be from 0, which is at this point, thereby the x value there, to 360, it will move up until it comes back there, and it moves in an anti-clockwise direction. So remember, this will be 90 degrees there. You move like that. So that will be in quadrant 1, that will be in quadrant 2, that will be in quadrant 3, and that will be in quadrant 4, which will be between 0 and 360 degrees. Now, this we call it a revolution, because remember, 360 degrees is normally called a revolution when we try to label our angles. Now, if you rotate r around the origin from 0 degrees to 360 degrees, for every angle, P has a unique set of coordinates, which you will surely understand. You saw with the previous example that at times it is the same values, but with different signs, meaning it is actually unique coordinates. For every angle, each trig ratio has a unique set of values as well. So for every angle that we have, clearly if I have an angle of 30, it won't give me the same values as if I have an angle of 45 degrees, and if I have an angle of 130 degrees and 180 degrees and 200 degrees. So that's what I really mean there. Now, if we define trigonometric functions, we're going to have 3 of them, right? Now, guys, with these 3, remember when we are starting with this particular concept of trigonometry, we also looked at the reciprocals, right? But now, when we get to the graphs or functions, we don't talk about reciprocals. Reciprocals is just trying to say, if maybe we are trying to find what 1 over cos is, we can give it a name and say it's sec. If we want to find 1 over sine, we know we can give it a name and say it's cosec. If we want to find 1 over 10, we can say it's cot. That was the big idea of the definitions and the concept of reciprocals. But with the graphs, we only have 3 of them. And the 3 main graphs is sine theta, cos theta, and tan theta. Those are the 3 graphs. The cos and the sine, they normally have some similarities with them, and tan, it's like an outlier. It's really one that is off in terms of the concept or the definitions that we are giving it under the concept of tan theta. So that's what you need to please note there. Right, so if I want to maybe look at the graph of y is equals to sine theta, remember that we're looking at this from the context of looking from 0 degrees to 360 degrees. So this is normally 0 degrees to 360 degrees. And this will look something like this. And that's how the graph of sine is going to look, where this point here is my 180 degrees, right? But if I look at now the graph of, I'm just going to write it in red, y is equals to cos of theta, right? The graph of cos of theta will then start from this point here. It will start from this point here, and it goes to that point, goes to that point, and then it ends there, right? Where this point will be 90 degrees, and that one there will be 270 degrees. So this is what we meant when we spoke about the concept of it reflecting, or rather rotating, to use the correct term, rotating from the x-axis in an anti-clockwise direction, right? So when it gets to the point here at 90 degrees, you can see that the graph of sine will actually have a value of 1, and the graph of cos will actually be 0. Hence, at that point, the graph of cos is 0, but the graph of sine has a coordinate of 1. And then, when you get to 180 degrees, the graph of sine is normally at 0 there, meaning the y value is 0, by the way. And then the graph of cos, we know it's not going to be 0, but negative 1, because it's normally between negative 1 and 1. And then we move on to 270 degrees. By 270 degrees, the graph of sine will be at -1. The graph of cos will be 0 degrees. And then the last point will be 360 there. At 360, the graph of cos will be +1, and the graph of sine will be a 0. So that's what we are looking at when we are trying to plot the 3 graphs. And then the last graph will be this one here, which is the tan graph. With the tan graph, it's normally drawn as arcs, right, where we have things that we call asymptotes, but we're going to look at that in great detail as we continue. So if I plot this, it will normally look something like that. This will normally look something like that, and then it will have one more arm going like that. So that's what it will look like, but this we will really talk about it in great detail as we continue with our lesson. So that's what I wanted you guys to please look at when it comes to the concept of trig functions. Remember, we said a function is when we have a mapping of one input value that corresponds with only one output. If I have more, then it's a problem. Also, we looked at the concept of a Cartesian plane, and we said, how do I measure angles on a Cartesian plane? Remember again that a Cartesian plane is normally divided into 4 quadrants, because it's more like a cross, right? As a cross, you know, there's 4 spaces that a cross normally makes, and each one of them, we call it a quadrant under the concept of trigonometry. And we label them using the Roman numerals. So between 0 and 90, you know it's quadrant 1. Between 90 and 180, that's quadrant 2. Between 180 and 270, that's quadrant 3. And then 270 and 360, that's quadrant 4. So that's what we are really trying to look at. And as you are moving across those quadrants, the coordinates of P will all be different. They will be unique. It might be the same number, but not the same value, because it can be 8 and -8. It's the same number, it's 8 and 8, but it's not the same value. Why? Because one is a positive and one is a negative. And that's what you need to look at. Also, as you are moving around it, we also know that the angles are normally different as you are trying to move, and they give us different ratios as you move from one quadrant to the next until the last one. Guys, stay tuned. We're going to look at this in great detail just after the ad break, and I'll be back with some more. Hi guys, welcome back. So we are still busy with the trigonometric functions. So just before we went to the ad break, I kind of drew the graphs for you just so that you can have a glimpse of what exactly is a trigonometric function and how it will look like, those 3 graphs that I actually showed you. Now we're going to look at them in great detail, and we're going to call them, by the way, parent graphs, right? We're going to call them parent graphs because at a later stage, we're then going to start changing some parameters, maybe shift it vertically or stretch it vertically. That's all we're doing at this level. So that's why I'm going to be calling it a parent graph. So I want you to please have that at the back of your head, because that's the language I'm going to be using as we continue. Now, so far we've looked at our Cartesian plane, which showed us the concept of ratios and functions. Now we're going to look at the concept of parent graphs. But the reason I'm saying parent graphs, remember, I'm going to change parameters at a later stage. And these parameters will be when I vertically stretch it or when I vertically shift it. But for now, let's go into what are parent graphs. Now, with parent graphs, you can see that with the graph of sine, right, it is normally between 0 degrees and 360 degrees. At this point in time, we don't really move on to the negative side of the x-axis, right? And I think you saw that with our Cartesian plane, under normal circumstances, we normally have -1, +1, and all of that in terms of the x-axis. But now, because it's trigonometry, our scale will be in degrees. So your 1 will be the same as like 30 degrees. But I'm not saying that's what the ratio is between the two. I'm just making an example of what the scale actually is in terms of trigonometry, right? So if you look at this, it starts from the origin there, and then it moves on up until it gets to a +1 there, which is the max point. It then goes down, crosses by 180 degrees, which is where the graph is 0, goes into the negative y-axis up until it gets to the -1 on the y-axis, and then it goes on to 360 degrees. So between 0 and 360 degrees, we call that the domain of this graph. Remember, domain is about where the graph is defined on the x-axis. From, as I said, the maximum value is 1, minimum value is -1. So between 1 and -1, that's where our range is going to be. Why? Because that's where it starts and that's where it ends, and that's where it is defined. So what pattern do you normally notice if we were to increase the values of theta? You can see that it is fluctuating. It's going up, it's going down, it's going up again. So that's the pattern that you will need to talk about there, right? So the domain of this will be theta is less or equal to 360 degrees or greater than 0 degrees. If I was to write this, now this is written in set builder notation, right? But if I write it in the way that I showed you when we're starting this, I will say theta is an element of, so remember, because of that bar, it means that the 0 and the 360 are inclusive. Therefore, this will be 0 degrees to 360 degrees, including the 0 and the 360 degrees, right? So that's where we use your square brackets. And we normally call this one rotation, right? Or people that are doing science as well will know that one rotation is also normally called a wave. And why I'm talking about that, we will see exactly where that comes in. The maximum value is 1 and the minimum value is at -1. I did show you that on the graph. It means then the range is -1 to 1. The reason why I'm starting from -1, guys, remember, in anything that you start with what is the least and you go to what is the most. Right? So you don't start from the maximum and say it ends at the minimum. No, it starts at 0. It goes to 360. It starts at -1. It goes to +1. So that's why I'm starting with -1 and you go to +1. So it's always the smallest to the biggest when you talk about both the domain and the range. So I can't really swap them around. You swap them around, incorrect. So make sure that you know that. And then the shape is normally a wave-like shape, as you can see there. Wave-like because it forms something like a wave. That's why I said people that do science as well will tell you that one rotation is normally called a wave. So if we increase the values of theta, you will need to look at what exactly is it that happens, right? So this there's going to be two terms that I'm going to also introduce, the amplitude and the period. but just stick to them and we'll talk about them later on. The amplitude is the distance from the midpoint, right, of the minimum and the maximum values to either the minimum or the maximum value. Now, I know this might be a bit confusing, but let's talk about this, right? This is my maximum value here. This is my minimum value here. The midpoint of this is going to be slightly there. So I'm saying the amplitude is the distance from this point, either from there to the maximum value or from there to the minimum value. It will be the same distance, right? So that's why I'm saying from either one from either one side of the minimum or the maximum. Then if the maximum value is 1 and the minimum value is -1, the midpoint, you know, it will be at y is equals to 0. Therefore, the graph has the amplitude at 1. An easy formula to remember this, you will just say A, which we normally represent it as the amplitude, is equals to 1 over 2 into maximum, minus minimum, right? So, and therefore, you will get what this is. So, what am I saying? With this, it's 1 over 2 into my max is 1, minus my minimum is -1. So, this is the same as 1 over 2 multiplied by 2, which is definitely equals to 1. So, you need to please note that. And then the graph of sine normally has a period of 360. Now, this brings into light the reason why I was talking about a wave, right? So, for one rotation to take place, or for one wave to be complete, it normally takes 360 degrees to do that. So that's what the period is. So the period will be the time in degrees, right? Or the distance in degrees it takes for the graph to complete one wave or to complete one rotation, however way you want to say it. So that's what the period is all about. And you will see that the period of sine and cos is normally the same. So the graph of this, the period is the time in degrees that this graph takes to complete one full wave or one full rotation. Now with the graph of course, it's a different story now. It's no longer starting at the origin. Please look at these guys. So the graph of sine, remember I said it starts from the origin, but the graph of cos starts from the maximum value, or maybe the minimum value if it's a reflection, but we're not there yet. So you need to please note that if it starts from the maximum, that's cos. Starts from the origin, that's sine. Therefore, if we increase the values of theta, you can see that it is also fluctuating until it goes there, and that's one complete wave. Because between 0 and 90 degrees, that's half a wave. Between 90 and 270, that's half a wave. Oh, so between 0 and 90, it's a quarter wave, not half. Between 90 and 270, that's a half. Then between 270 and 360, that's another quarter. 2 quarters and a half, they make a whole, which is one complete wave. Now, the domain of this is between 360 and 0 as well, remember that. And I said we can always write this as theta is an element of my 0 degrees in square brackets to 360 degrees in square brackets again. And then the maximum value is also at 1 and the minimum value is at -1. Then the range of this, because of the minimum and the maximum, it will be from -1 to +1, right? Now, the shape is also still a wave-like shape. The amplitude of this is 1, because remember, max is 1, minimum is -1. So it's still the very same thing if we were to use that formula. And then I did mention that they have the same period of 360 for them to complete one full wave. And then the last graph that we're looking at is the graph of tan, right? And the graph of tan is actually going to be something like few arms that we are drawing, right? But now, what you need to be very, very careful of when you're drawing the graph of tan is this dotted line of mine here. You see this dotted line of mine? We call this the asymptote. Why asymptote? It's because it's where the graph is going to approach but never cross, right? So the asymptote you will see when you do more of the functions. An asymptote will be where the graph kind of tries to approach, it approaches, but it never gets to that point. So we normally say with this one, as theta is approaching 90 degrees from the left, the value of y approaches infinity. So it normally goes close and close to it until it gets to infinity, which you know. Me and you don't know what the value of infinity is. It can be a billion, it can be a trillion, it can be a quadrillion, a fabillion, anything that has to do with the biggest number you can find out there. That's what infinity is about. So those are the numbers you need to please know. So an asymptote will be where it is really approaching but never to touch. So that's what an asymptote is about. Now, the domain of this is also from 0 to 360 degrees, but what I want you to now note is this has no maximum value and it has no minimum value. I mean, if I go back to my graph, this arrow, I just said to you, as it is approaching that 90 degrees, the y value is going to infinity. So to infinity, it means that it never ends. It is not stopping. It is continuing indefinitely. That's what the arrow means. Similarly, with the negative infinity down there, as it is going down here, it is going to negative infinity. So that means what? Our range is going to be from negative infinity to positive infinity, because we don't really know where it starts, we don't know where it ends, but we just know that it starts from the smallest y value, and it ends by the largest y value. So that's why it's negative infinity and positive infinity. This shape is definitely not a wave, like I did tell you that, and you just saw it as well. There is no amplitude. Why no amplitude? Because there is no max and there is also no min. So you can't have an amplitude if you don't have a max and a minimum value. But there, if you look at the graph, the pattern repeats after 180. So let me show you what I mean, right? So from 0 degrees there up until 90, you can see that it is up there, right? And then from 90 up until 180, it is down here. Now from 180, it starts as what it was initially looking like, right? So it is repeating now the pattern to go up there, and then it goes down there. It means from 360 again, going to the right, it will also go up like that and go down like that. So that's what I mean when I say it now starts to repeat its pattern after 180, meaning the period is actually 180. So for it to complete one pattern or one revolution, it is actually, or rotation I mean, it is actually after 180 degrees. Now with the amplitude, guys, remember that on the Cartesian plane, if I look at tan theta and I want to find the tan theta here, and my theta is 90 degrees, you can see it will lie on the y-axis, and on the y-axis the value of x is 0. The value of y, we might have it. In this instance, our y is 10. If I want to solve this, tan 90 degrees is 10 over 0. I dare you to press your calculator now and say 10 over 0. If you get an answer, I promise you, I will give you everything you want in life. But it will actually be undefined. So that means the graph is not defined at 90. Hence, we call this the asymptote. And the asymptote of this graph is at 90 degrees and 270 degrees. So guys, that's what we are just talking about there. Remember, sine and cos, they have period, amplitude, maximum, minimum, right? Range and domain is always going to be there in any function. But with tan, it has its own period. It has what now we call asymptotes. It does not have a minimum or a maximum. It also does not have what we call the amplitude. But instead of the amplitude, it has the asymptote. So that's what you please need to note there. Guys, I'll be back with some more, and I will now start drawing the graphs so that you can see what they look like. I will draw them and also try to change the parameters for you to be able to see the bigger picture of what the graphs are about. Just stay tuned and we'll be back with some more. Hi guys, welcome back. So we are still busy with some functions. So we looked at the parent functions. Remember I said I'm calling them parent functions. Why? Because we're going to start changing parameters and see exactly how does it happen that I want to stretch my graph, or I want to maybe vertically shift it or something like that. So that was the main thing that we looked at. So our concept map, as you can see on the board, has been about our ratios, our functions, and then we looked at graphs. Now we're going to look at the actual thing, which is changing those parameters. Exactly what does this mean? That's what I want us to talk about. So the parent functions in the interval 0 to 360, remember there's 3 of them. I said please don't think about the reciprocals here, because we're not going to talk about that under graphs. And then from there, if we then look at the general functions now, right? So look at the terms, guys. These are parent functions. These are general functions. Why general? It's because this value that I have here is what normally determines what my maximum and my minimum values are, right? Similarly with this one here, it normally determines what the midpoint of the maximum and the minimum value is. And that's what we're going to talk about in terms of it being a general function, right? So with a vertical stretch, you can see that to move from f of x, which is sine of theta, to go to f of x, a sine of theta, the a represents a vertical stretch, right? Similarly with the cos graph, to go to there, the a represents the vertical stretch. For wave-like functions, the amplitude normally changes when the value of a changes. But I want you to remember something about a. Remember I said a is the distance. So distance, I know that you know this. Distance is a scalar quantity, meaning it does not have direction, right? Even if I give you a negative value of a, you disregard the negative. Why? Because we only want distance. So you can't say I traveled negative 20 kilometers. That would really not make sense. I traveled 20 kilometers, right? Then I will ask you, where were you going? Then you will tell me, no, I was going to Johannesburg, I was going to Pretoria, I was going to Northwest, or anything like that. But that has to do with the distance that I traveled. So a is the distance, meaning even if I give it to you as a negative, you don't really regard the negative, please. That's really important for you to note. So now one question that we'll need to look at to draw this graph, I will say sketch the graph of 2 sine theta. So firstly, before you do this, you will just need to try and use a table. You remember when you were doing your straight line graphs in early grades of doing maths, and then you will say this is theta, and then you will say this is my y, right? You will use different values for this. You can start at 0 degrees, go to 90 degrees, go to 180 degrees, and then go to 270, and then lastly go to 360 degrees. This will inform which values of y are these values going to correspond with. And then you know that if theta is 0 and I have 2 sine 0 degrees, this will also be 0 as 1. That's the y value. If I have theta as 90, then it will be 2 multiplied by 1 because sine 90 is 1, which will give me 2. 180 will be at 0. 270 will be at minus 2, and then 360 will be at 0, right? In terms of a graph, this will look something like this, right? So you can start with looking at it from this perspective of using the table, or you can look at it from the perspective of using the parent graph. The parent graph is the dotted one, right? So you can see the dotted one, it normally starts from 0, the maximum is at 1, and the minimum is at minus 1. But because of these two, which I said informs the maximum and the minimum, we are then stretching our maximum to be at 2 and our minimum to be at minus 2. Hence, it is going to go up until those points there. And that's what a vertical stretch is about. But let's look at more graphs just to try and make sense of this. Now, so with this, some few pointers to look at: the vertical stretch of a basic graph of y is equals to sine theta will be what the question wanted us to do. And the minimum value, the maximum value here is going to be at 2. The minimum value is going to be at minus 2. And if I know that, it means that my range is going to be between minus 2 and positive 2. And then remember the concept of the amplitude. It will be 1 over 2 into 2 plus 2. I'm saying plus because it's going to be minus that. And this will just give me 2 plus 2 is 4. And then if you have it, it gives me 2. Hence, I said this value normally represents the amplitude, but only for the sine and the cos. Remember, the tan does not have an amplitude. Now, another graph will be sketching the graph of 4 cos of theta. 4 cos of theta, you're also just going to be using the same thing as what I did with that one, right? So theta and y, theta represents our x in this instance. Then you can use 0 degrees, you can use 90 degrees, you can use 180 degrees, and until you get to 360, because remember, we're only looking at the domain between 0 and 360. When this is 0, we know that the answer here is going to be 4. When it's 90, the answer is going to be 0, because cos of 90 is 0. 4 times 0 is 0. 180, cos of 180 is minus 1 times the 4 will be minus 4. I think maybe you will be thinking I'm making these numbers up. Let me just show you guys. So remember, cos of 0 is going to be 1. You times that by 4 because there's a 4 in front, right? Then cos of 90, it will be 0. You times by 4 gives you 0. Then lastly, cos of 180, which I also used, will be minus 1. Times it by 4, it's minus 4. So please, that's where the values come from. But if I draw this, the easy way, by the way, of doing this is just to stretch the mother function, right? Or the parent function, we call it. And to stretch it, it means this 4 says that you stretch your maximum to be at 4, and you stretch your minimum to be at minus 4. So it was at 1, it gets stretched to 4 there. Therefore, my amplitude now becomes 4 and no longer 1, like with the original parent function, right? If we analyze this, you know that this is a vertical stretch of the basic graph of cos of theta, and the maximum value I just said will be at 4, the minimum value will be at -4. And then my range will be between -4 and 4. And if I want to find the amplitude again, remember 1/2 into 4 plus 4. 4 plus 4 is 8. Half of that will definitely be 4. But you can just look at the number in front there. Now, with the vertical stretch, which is actually for the tan graph, you need to remember there is no amplitude. I'm not going to be saying A is the amplitude. It's only the amplitude for the sine and the cos graph, right? So you can see that the stretch where theta is 45 degrees, it will then be 45 degrees is equals to 1, because that's how you normally draw this graph. All right, so let's look at if we were given a question to sketch this graph of tan, right? You will still be using the very same concept as what we've been trying to do with the sine and the cos, where you're going to plot the values of theta, which are our x values. So it's 0 degrees. Just for variety, I'm going to use 45 degrees and then use 90 degrees. So remember, with 0 degrees, it's going to be 3 times 0, which is still 0. And then 45 degrees, from special angles, remember tan 45 degrees is 1 times 3, it will be 3. And then we know that for 90, it is undefined, because remember, that's an asymptote of the graph. In terms of a Cartesian plane, this will look something like this. Now, my blue dots actually show where the graph is going to be. So my graph will roughly look something like that if I've vertically stretched it. And then it will go up there, go there. It will just need to pass there. Just assume that it is passing there, because I'm drawing by freehand. And therefore, it will look like that. So that's how my graph is roughly going to look like. But remember, you will need to sketch it really nicely so that it shows that it is curving and not straight like mine. Now, the other graph is sketching the graph of -3 sine theta. Remember, I did tell you that the minus is just so that you know that there is a reflection, not necessarily that the amplitude is a -3. No. So from the original graph, which is sine theta, we're going to first stretch this 3 units and then reflect it about the x-axis, right? So the original graph is this one. You stretch it, that's number 2, and then you reflect it. And then my graph will look something like that. So that's really the main thing. Now, if you just look at this, it's actually the reflection in the horizontal axis, which is the same as the x-axis. I'm not really calling it the x-axis here because we're normally using theta, and also you will then trying to mistaken that for x. Vertical stretch of basic graph, you know, sine theta, and the maximum value here is going to still be at 3, the minimum value will be at 3, and then you know amplitude will be at 3. And then our range will be between -3 and +3. So far, guys, this is all that we've done. We've looked at the Cartesian plane, the ratios, and the functions. And then we've been talking about the vertical stretch. Now we're going to talk about the vertical shift. With the vertical shift, it's when we now include the plus q, right? So the plus q is actually what represents the vertical shift, right? Shift, you know, is translating this graph a certain number of units up, a certain number of units down. And that's what we are looking at there. So with all the three graphs, remember the sine graph will be sine theta plus q, cos theta plus q, tan theta plus q. We're not really looking at the stretch for now because we've spoken about a stretch and I showed you what it looked like. Now, if we look at some questions that want us to do this, they say sketch the graphs of f of x is equals to sine theta plus 2 and cos theta minus 2. Now, already you can see the plus 2 because when you talk about the vertical stretch, guys, going up or down, we are actually trying to say the plus is the positive y values and the minus is the negative y values, right? So going up, it's plus 2, going down, it's minus 2. So that's what you will really need to look at. So in simple terms, the sine graph is shifted 2 units upwards. The cos graph is shifted 2 units downwards. So you need to think about that. If I draw this graph of mine, so let me maybe try to do that for you. If I draw this graph of mine, it will be, firstly, you draw the mother graph, right, or the parent function. From the parent function, you will draw this one, right? And then I will go to my red, and then with the cos graph, it will look something like this. That's the mother graph in roughly, and then you will be required to then draw this one. But I will leave you to be the one who does this particular question. So just a quick recap of what we've looked at, guys. We've looked at some parent graphs, a vertical stretch and a vertical shift. We looked at the concept of a Cartesian plane, which was the main thing that we're also trying to put across. With this, we looked at the functions, we looked at the ratios, and that's what we just needed to look at. So guys, with functions, there are 3 main concepts that most of the time you will be asked to state. 1, the amplitude of the graph. 2, the period of the graph. 3, sketch the graph. And then you know the 2, which is the domain and the range, they all there in every function that you have. You will need to also know that. In most cases with us, right now we are actually going to only look at from 0 to 360 degrees only. Maybe we can stretch it to 720 degrees where it's 2 complete waves. But we will never go to the negative side. That's one thing you need to know about that. And then you look at the vertical stretch and the vertical shift and what exactly does that mean. Those are things that we just needed to look at. And then the next lesson we're going to have is going to be the revision lesson, right? With the revision lesson, we're going to then be answering more of these questions just to try and put across what exactly does all of this that we've spoken about mean. But from me to you, the mathematics guy, I will see you guys next time. Cheers, everybody.